that the sketch is made, and that this is the precise set of no, yeah. So you are here for precise. So, to those of you that did not know that the plan changed, you came to a quite similar in some aspects presentation. So the thing is that Philip got stuck between airports at the moment, and just switched so that he can have also the sort of relaxed. Yeah. All right. So how many of you are doing CFD? Okay. What do we do in CFD? We simulate flows. For example, the flow around the. Who of you has some knowledge of structural simulation? Okay. So what would we do in a structural simulation? We would check if the airplane gets by some load, will it break or not? So you're doing CFD, you're doing CSM. Who of you is actually simulating both at the same time? Okay. Already some of you. So what we want is to instruction fractions and similar couple problems that we take the one domain and we compute the solution grid that we use as boundary conditions for the other domain, and so forth. So this is the partitioned approach that's coupled with. Now, the view that said that you're simulating both at the same time. Are you using one code that does everything, or do you reuse? Who uses one code that does everything? Okay, and who does the partition approach? Okay, interesting. So this library that I talk about, FSI, lets us reuse components that we already have. So you have your OpenFOAM solver, you have your calculate solver or solid, and say, okay, I already have it, but I need to develop something from scratch. And what it allows us is to go from CFD world to the framework, that's not mapping. And it also allows the solvers to communicate. Very briefly, the features that this library can give you, meaning that it takes care of them without you having to code any condition. That takes care that the solvers find each other and communicate, and they communicate in a fast and efficient way. And fully parallel. So if you have your simulation running on a cluster, and maybe you can have your simulation running on different clusters, they will make connections only between the MPI routes they have. Then it gives you the ability to map from the finite volumes mesh and the integral made very fine to the FEM mesh, the tetrahedral and product force. And it gives you algorithms that can do this in high accuracy and in at least second order conversion. It also gives you algorithms for cutting schemes, and this is something that I'd like to show you in the second part of the presentation. And it allows you to not only just exchange values once and move on, but allows you to iterate and reduce the number of iterations as inflation continues the synthetic size when it was learns from the past. The new feature is that you can also do time interpolation, meaning that the solvers can operate in completely different time scale, and they don't anymore need to do them. This is coming with like it is already there, but it is becoming a third class feature besides the bring later. So what people do with FSI, quick example. I don't really know the people that did this simulation. So here you see some ocean energy generator that here complex two components, wings, and I think they are simulated using OpenFOAM by FSI. The second thing that people do with FSI is coupling it to particle codes for pre-structure interaction. Luxembourg, they have their particle code next to them, and they have OpenFOAM for the flow, and they also have calculates for the structure. So they have this lab that is granular particles. And as a final FSI example, someone on YouTube uploaded a simulation that uses two-phase flows and the text plot. And yeah, you see that this is possible. Now, I showed you here only pre-structure interaction examples, just because the theme of the session is about pre-structure interaction. I would actually divide it specifically talk about that. However, this is not the only application that we do with precisely. They couple transfer code, they couple chemistry, solver. In this talk now, I'd like to talk about the theme, how you can use all this structure in two different levels. First, I'd like to focus on the perspective of the developer. You're developing some code yourself, like your OpenFOAM or your in-house code that you have in your lab, that maybe you're developing because it implements some novel features, right? And how you can actually use the PRECICE API, so it's the library directly in the code, and to solve such a couple of things. And in this case, we will just show Python codes because that's the interesting. Then, in the second part of the talk, it will be most familiar for some of you, because we will directly use some components that are already available and a couple of important calculations for an actual relatively realistic situation. Okay, so the slides that I have here and more material, including the poster I'm presenting today, you can find with some code, so in case you get lost a bit, you get. Okay, so organizational notes. You don't get tables in front of you. I don't see anyone with a laptop. That's good. You're not expected to try things live. Anyway, the session is being recorded, and I will be here for the rest of the workshop. If you want, I would be really, really happy to just sit with you and try what you want to play together. Please feel free to interrupt. We are a bit tight on time, but I think we have time for questions. Let's see. And for those of you that may want to try things out later, I have some USB sticks, a live Ubuntu distribution that have everything that has already installed, and you could just plug it into your laptop. If you are joining remotely, you can find a virtual machine that again has all open source solvers that support it. And I know this may be giving the false impression sometimes because I'm wearing a t-shirt with a nice logo and everything sometimes fancy. It's not commercial, it's all open source code and developed at universities, and we're just quite like developing it. And thus, all we do is also talk together. Also the codes that I'm using for the calculates there also resolved. Okay, so part one. How to use the API. We will do everything with PreCICE version 2, Python 3, and PreCICE Python 1. I think we don't need OpenFOAM, don't need that. We will not solve any CFD. We'll do something simpler, way simpler. In this 2D domain, we will solve something that looks like no problem. This has a boundary condition, this in this blue line, that essentially gives random numbers, like injecting fluid with different velocities. And then this square solves something like a convection problem. What you will see is that the flow is coming from the right and it's propagated. We'll have two codes, Python code, one is called generator, and the other is called propagate. What we will show here is the simplest possible couple problem. In the sense that it will be unidirectional, meaning that we will be only sending from the generator to the propagator and getting up the bucket. And yeah, it would by definition be an explicit couple, not by parallel. Let's look at the code. This is the call of the generator file, this boundary condition. Generally, what do I want from you now? I don't want you to understand every Python specifics. I just want you to understand that it's a code, right? And what more or less we expect. So what is going on here? We import some libraries, apply, understand. In this case, we generate a mesh that is just 30 points per linear space. We set some time step size and some initial time to start the simulation from, and then we have a time loop. And essentially, we say that till the universe burns down and generate data and compute a new solution. This is just assigning some random numbers to this. Then advance the time, and once we reach some time, in this case, we want to stop the game. So this is a typical structure that you find in every solver. You have a time loop, and you have a mesh, and you have some boundary conditions. The propagator, so the square that propagates things, this is slightly longer, but it's exactly the same. So we define a mesh, 20 by 20. We initialize our solution to 0. We set our time step size. We set boundary condition that just depends on the height of the mesh. And we apply some convection between that does not matter. And again, at some different time, it stops. So what would happen now if I run these two codes there? Two independent codes, right? So I don't know how much anything, but if I run Python 3 generated to 5, I see that okay, the one code runs nothing in it. If I run the second code, again, it starts and I get a window that shows me essentially that this is the boundary condition that depends from the distance and the propagation. And this is the results I get. So this is uncoupled. Okay. Any questions so far? I guess that was clear. Yes. I cannot hear it. I don't think I can make anything larger, but if you want, now would be a good time for everyone to look forward, I guess. You can also open the slides on your phone if you like. I'm sorry for. Okay. The video was the well, yes, I know. But this is nothing. Nothing much happening. So you just run Python 3 in the script, and then it just shows some dummy out. Okay, but let's now go into the more interesting part. So PRECICE is a library, and it's a C++ library that we can also use with Python, with C, with Fortran, with Julia, with MATLAB. There are bindings for all this language. So similarly to how we imported NumPy, we can import PRECICE. And after defining a mesh, we can set up our coupling mesh. So we say that now that we are in this generator.py script, okay. I hope you can hear me better now. So we say that this is one of the two participants. This is called now generator. And we need to give it some configuration file that is the same file for both participants. How are we doing here? Okay. And I will only talk about this, the details of this file much later in the second part. As a parallel library, PRECICE uses the MPI communicator of your solver. So it needs to know every time that it is being called by every MPI process, which process this is and how many processes are in the MPI board. If you don't understand what this is, don't worry, it's not relevant. Then we need to construct PRECICE. We need to call the constructor, and we do this by calling the PRECICE.interface, and we give this the variables that we just created. All right. Now that we have some object to work with, PRECICE is initialized, more or less, we need to define what are we actually coupling, where are we coupling, and what. So PRECICE defines some buffers, some additional coupling meshes. And we usually define one per participant. And we're then going to map between the two. So here we define a name that is called generator mesh. This is defined also in the configuration file of PRECICE. PRECICE works with some integers that identify the mesh, and we call this get mesh ID with this name. This is becoming much easier in version 3. And we define the coupling mesh. In this case, we're just taking the complete domain. So from 0 to maximum, we say we couple this point. And we call set mesh vertices on this PRECICE object. So we have constructed PRECICE, we have created a mesh, and similarly to MPI, we need to initialize it and finalize it. And we do that before and after the main loop. And inside the loop, every time we get a new solution, we need to advance the coupling. We need to say, okay, the solvers did a time step, but now the coupling itself needs to perform this time step and assigns the variables to the variable. Now, if you paid attention earlier, the one solver was stopping at 0.1 seconds, while the other one wanted to continue at 0.2 seconds. So if we have such a coupled simulation, how do we decide when to stop? So the answer is that we delegate this decision to PRECICE. So you go into your time loops and change the while true or anything else to while PRECICE is coupling ongoing. So PRECICE will set the maximum time for the complete simulation. And regarding time stepping, we of course need to make sure that at some point the two participants synchronize to exchange data. This is not necessary if you use the time interpolation, but let's assume you don't have this feature yet. So what you do is that you take the minimum of the time step you want to do and the time step size that PRECICE allows you to do, because it tells you some coupling time is approaching soon. Okay, and we're not complete, but at least what you should see now is that when you try to run again Python 3 generator.py, the solver starts and you see some PRECICE output and the solver waits, and it waits until something else appears on the other side. How do they find each other? They just exchange one address via some file in a predefined location, but everything else is happening in memory. So what is happening then is that the one is computing, the other is waiting, getting data, and computing. But still, even though the two solvers kind of synchronized, they don't really do anything interesting yet. We just see that the propagator still gets the same constant boundary condition. What did we forget? We forgot to just give the data that we want to couple, right? And until now, this looks just like MPI, but I promise it is much more elaborate. So we want to exchange some data, in this case, this color that you see. We give it a name. And again, we find the corresponding data ID, the number that it corresponds. And we call a function that is called write block scalar data to update essentially extract the boundary values from our solution and give them to a PRECICE buffer. And on the other solver, of course, we are also doing a read instead of the write. And this happens, the write happens before advance, and the read happens after advance. So the advance is what, in a black box way, updates the value, does the communication, does the mapping. Okay, so now I'm running two terminals. I forgot to clarify that. The one terminal, I'm starting my generator. It starts, waits there for the other participant to appear. The second terminal, I'm running Python 3 propagator.py. And once it starts, they start communicating. And you see that now every few time steps, I'm getting a new update. How often I get such an update? It's of course uncontrollable. All right. As a last thing, compared in respect to the API, how does this configuration file generally look like? So this is not the file itself, but because it's sometimes complex, we have created a visualization tool. Actually, my colleague Federic Simonis did that takes this XML-based configuration file and makes some nice drawings of that. So what do you see here? Hopefully, this is that you have the boxes. This one is called generator. This is called propagator. And you also have here a polygon with the same name. So this is the code. So The code is writing something that is called data, we call color, we call velocity, displacement, whatever. Some mesh that it defines, because it's a solid line. And this mesh, this buffer is exchanged, it is sent to the other side. See here the dashed line. And then there is a mapping between this mesh and the mesh that the other participant provides, the propagator mesh. In this case, this is the simplest possible mapping, that is find the nearest geometrically point on the other mesh and take the value of that. But you can imagine this is also very naive, but it is very costly. And then the propagator reads data from this mesh. You also see that we have configured a serial explicit coupling. Serial means that the one runs after the other with some wait time between. And the one uses the update solution of the other. Think of a Gauss-Seidel solution method. Explicit means that there is no iteration. And you also see that the generator goes first and the propagator goes second. And how they communicate here is with TCP IP sockets, because this is a very robust method. If you are on a cluster, you can also use MPI ports. All right, so now would be the first opportunity for some question. Yes. If you have, so the question was, it looks simple if you have just two single core codes, right? Single threaded code. What happens when you have some multi-threaded, multi-core code? So this is one of the unique selling points, if you will, precise, that the whole communication is happening completely peer-to-peer. Meaning that you have your fluids solver running in 100 cores, and you have your structured code running in 10 cores. And this means essentially that every core of the, assuming that you're coupling the complete domain with A, in some case, related. This means that every solid core process communicates with 10 other only processes. And it does not communicate with the rest because it does not need to. So typically, this is not the bottleneck of this operation. So your solver itself usually is much easier doing other things than the time it spends doing this implementation. And everything is, of course, not located. Another question, maybe. Okay, maybe later. So, my fonts are a bit off here. Please excuse me for that. But what is the big picture? So, we have this codes. We have some safety solver, could be OpenFOAM. We have some FEM solver, could be Phoenix. And each of them starts normally. I start a terminal and I start my solver. And each of them calls PRECICE separately. So OpenFOAM calls PRECICE, one process. Phoenix calls PRECICE, another process. Now, you could do all this work that I just showed in a summary to call PRECICE from your code. You could hard code all these commands into OpenFOAM, for example. But that would not be very user-friendly. So for many popular codes, we just create such adapters. So we write the code for you. In case of OpenFOAM, this is a plugin. In case of other codes, this may be some example. So that you don't need to write code. And you can couple essentially anything. You can couple open source codes. You can couple your own in-house solver that may then even be commercial or whatever. You can couple particle solvers. You don't always need to have a mesh. You can go from the particle world to the mesh world. And you can couple arbitrary many without writing any additional code. So this is sometimes done. And you see here some of the examples of codes that we currently have. You will also see some later. All of these are open source codes. So what does an adapter do? In case of OpenFOAM, the adapter is a function object. As you know, function objects, there's currently another talk of the session showing some of them, is a plugin for OpenFOAM. And what it does is, first of all, it links to PRECICE. It extracts boundary values from OpenFOAM and gives them to PRECICE. And also does the reverse. It takes new values from the PRECICE buffers and applies them on boundary conditions. It also manipulates the time, so it keeps some checkpoints, because when you do implicit iterative coupling, you need to go back in time and repeat your computations with better boundary conditions. And it also adjusts the time steps out. So it tells OpenFOAM, no, you need to slow down. If you now wanted to start with any of these codes, you would go to the PRECICE website. I would say, for which we are quite proud for all the work we have put there. And the first thing you should do, especially as OpenFOAM users, is to run this quick start. This assumes that you are running some Ubuntu system that typically you can find, and shows you how to install the latest OpenFOAM, the OpenFOAM adapter, and run a first simulation that is very close to an FSI simulation. So this also makes sure that you have everything installed. Today, however, I want to show you something a bit more elaborate. And it's a case that many of you may have seen. You have this channel flow, essentially, and in the middle of the channel, you have a beam, which is elastic. So as the flow comes by, you have this deformation. Imagine some seagrass in the sea, or this wave energy generator. This is a PRECICE tutorial that you can find on the website and you can run. And we have made the PRECICE tutorial so that you can run any combination of available solvers. I will show you today how to couple OpenFOAM and Calculix, but you could even just couple OpenFOAM and Dune or Nucleus and PL2. And you can even couple solids for foam. Because solids for foam has also some solid solvers, and that was also some contribution by Philip Carty that enabled solids for foam to run with the adapter. And the nice thing there was that he said, hey, I have this nice solid solvers, but with solids for foam, sometimes I need to do the same work again to couple different fluid solvers. But with PRECICE, I essentially get access to way more solvers that are already coupled by default. So I think there is quite some synergy there. Very nice. And something that I found recently is that OpenFOAM itself actually has a structure solver, a very, very simple one with extremely linear material. But so you have all these different combinations. And the interesting thing is that we did a lot of work to tune the cases so that they give the same results. Here you see different combinations. You see the two lines, two groups of lines. The two groups are just incompressible and compressible fluid solver. Of course, there you would get different results, but among incompressible and compressible solvers and different solid solvers, you get the same result. So this also gives you the opportunity to quickly prototype some simulation. You say, this calculus does not have this feature, I want it. Maybe I write something in the output quickly. Okay, so again, PRECICE version 2. Recent OpenFOAM, it works with many recent versions of the ESI and many recent versions of the foundation in version-specific branches. You need the adapter, calculus, and the calculus adapter. Actually, just the calculus adapter because it's just a modified calculus. Okay, so every tutorial, every case in PRECICE has this configuration file that I just explained. And then you have two directories. You have one directory for your OpenFOAM case, and you have another directory for your calculus case. In your OpenFOAM case, you need to modify the boundary conditions of, for example, the velocity or the displacement, something else, to be usually fixed value or fixed gradient, depending on what kind of coupling you're doing. Dirichlet, Neumann, Robin, and so on. You need to set, of course, some mesh motion solver because you have this moving mesh. It works with displacement Laplacian and with this RBF mesh motion solver that is part of solid component. And in the system directory, you need to enable the adapter in the control bit as a function object. And you need to give a small configuration file that I will explain where you say what you are talking with spaces and so on. And for calculus, you have typically such a parameter file, this lab.in, which, okay, if no calculus, you set it up. And again, some configuration file for the what you have. So for demonstration cases purposes, I took this tutorial and made it a bit shorter so that we don't get multiple oscillation, but we get like one period. And I switched from the nice coupling scheme to the simplest one to show you some limitations. And then compared to the tutorial, I lowered the density in the solid because more interesting phenomena happen. Okay, so let's configure OpenFOAM. For the velocity, you need to set moving wall velocity because we are coupling displacements and forces, but we're not coupling the velocity of the mesh, which is completed by OpenFOAM. This is to make it essentially more interchangeable with other solid solvers. You have to set a fixed value for the point displacement because we are setting values for the displacement that we get from the solid side. So the fluid computes forces gives it the solid computes again the deformation with the displacement and gives it to the fluid. And we also configure the displacement Laplacian mesh motion solver for in the dynamic mesh. Then, similarly to other function objects, we just go in our control bit, and under functions, we give some arbitrary name here and say that this is the PRECICE adapter function object that links to this library. This is the adapter that you compile separately. And then you need to configure the OpenFOAM adapter that links again, tells you where to find the PRECICE configuration file. Otherwise, OpenFOAM does not know that this even exists. And typically, you have this in the parent directory of your two cases. You say which participant you are fluid. And the OpenFOAM adapter is structured in a way that it has different modules for different kinds of simulation. It has an FSI module, a constant heat transfer module, low coupling module. So you enable the FSI one, you can also enable multiple ones. And then you say which are the interfaces you are coupling. In this case, we only have one interface. It's like the solid surface. This is that patch in the OpenFOAM domain. And we just give it some arbitrary name. And we say that this maps to the fluid mesh of PRECICE. It includes some patches. In this case, we've named the patches plot in the block mesh. And then we say these are interface located on the centers or on the points of the face. In this case, it's located on the face centers because we are exchanging forces and self-displacement. So we will be reading displacements and we will be writing forces. Reading and writing also means perspective of PRECICE. So I give something to PRECICE, I get something. In this case, we are coupling OpenFOAM, that is an incompressible solver. And to compute forces in an incompressible solver, you also need to have some density, right? Which here we just calculate. Of course, in a compressible solver, you don't do that. Similarly, in the calculix adapter, you have, you say that I am the solid participant, like this for historical reasons, and I have some interfaces. Here is one interface that is called solid mesh that is on the nodes. And it has again some patch of calculix that's called surface. It reads forces or potentially more things and writes displacement or potentially. Again, where is the PRECICE configuration file? Configuring PRECICE, we see that we are exchanging from the fluid, we are sending forces to the fluid mesh that is mapped with some more elaborate, accurate mapping to the solid mesh that is exchanged to the solid and then read. And in the reverse, we are doing, we're sending displacements that the fluid again maps back and prints them. Okay, so this is a serial explicit scheme. And how does this configuration file looks like? It's XML based. And you just have some tags where you say this is some data, that's some vector data with these names. These are two coupling meshes with associated to those data collections. And we have two participants, the fluid and the solid. In this case, the most important part is that we are reading and writing these two fields over these meshes, and that we are defining two mappings, in this case, using radial basis functions, with a direction from the fluid mesh to the solid mesh, and in this case, as a conservative mapping. This means that when you're mapping force, you're going from the many points to the few. Well, you need to integrate a bit so that in the end you get a total force. And you define how the two solvers communicate. That's the default. And we are defining a coupling scheme that is here a serial explicit. What is important here is that we are defining who goes first, fluid and solid. They go up to 1.5 seconds. They exchange the values every 0.01. And they exchange forces and displacements over these meshes in this direction. Not important to understand everything else. And I apologize for the size again. But what you do is that you start terminals, you start normally, you start calculus normally, and eventually you see that OpenFOAM crashes. Why does it crash? Which of the buzzwords that I said so far was problematic? What did I change in the beginning compared to the tutorial to show you something? I'm using an explicit scheme. An explicit scheme means that I'm exchanging velocities, exchanging displacements, but I'm not checking if they are converged, if I have the same values on both sides. Of course, I would need to iterate. And if I don't, in this very simple problem, I guess I get this equation that, yeah, the mesh breaks, everything breaks. Essentially, here what is happening is that the ground number is okay. So what we did so far was we had our flow simulation. We were computing some new solution. We were giving it to the solid Alphanix that was giving us some new displacement, and we were just moving to the next time step. Now, we want to do something different. We want to iterate before we move to the next time step. So we add here an acceleration or post-processing step. And now we are getting to the more interesting part, where we're going to compare such different schemes. So let's try the simplest thing, that is a serial implicit coupling that, again, it has the order to first solid second, at the same maximum time and coupling times inside. Exchanges the same data, but now it iterates and checks for convergence. So we need to set some convergence measures and some maximum number of iterations for, something like that. And then we will be doing a very simple constant under relaxation, an under relaxation with a constant factor. In this case, arbitrarily 0.5. That's probably not the best idea. But still, this simulation not only continues, but completes and reaches some steady state. So even this, in this steady state, is a physical. And the problem with that is that if the first thing took like 2 minutes, this took maybe 10 minutes. The backward and that was because it was doing too many iterations. So the question is, can we do better than that? So the first thing that typically people do here is to still do under relaxation, but update this relaxation factor dynamically over time. So we start again with the 0.5, the relaxation factor, and we let the size choose a new relaxation factor as the simulation. This is happening with this item. And if we run the same simulation again, see that we get the same results, but we get them faster. In total, on average, we had 150 time windows, and we had to do like 3.85 times more iterations on this time window. So like in the range of 400 iterations to reach the state, the constant. And with ICANN, we drop again. Normally the difference is stronger, but this problem, first of all, is not so strongly coupled. So it's a relatively easy problem. And second, it's reaching a steady state. So after a while, you get fewer iterations anyway. That's different between. The next and concept thing that sometimes you see people doing is the underscore acceleration. This is this quasi-Newton ILS. There's also the Broyden method. And if you do that, you have again to define an initial relaxation, but you also define a preconditioner, some filter, and reusing some number of iterations in time steps. So This uses information from the past of the simulation to approximate the gradients essentially that you need to compute the new boundary condition. Using this, we drop even further the number of iterations by a lot, I would say. And we can even do better. So far we followed serial schemes, but there are also parallel schemes, meaning that in the serial, one was computing the other weighting, then after it was done, the solid was continuing, and so on. In the parallel schemes, we do something like a Jacobi solver, where we exchange values once, we compute the next solution, we exchange values once, we compute the next solution at the same time. This can be faster sometimes. By the way, it has nothing to do with MPI parallelization. Both work with parallel solvers in parallel. And the only thing we need to do is to change the serial implicit scheme with parallel implicit beside. We've written no code, right? We have only changing configuration files that we are trying different algorithms. And we drop even further. We're still using quasi-Newton. All this, in principle, every combination is a different algorithm in literature. But here you can essentially configure between serial, parallel, IQM, and so on, like that. And if we were to compare a bit what is happening here, you see that the constant under relaxation starts at like 9 iterations per coupling time window, and then the column reaches some kind of state, so it reduces. So these are this purple lines, and here you have essentially time, and here you have number of iterations per coupling time window. And then just by going to IQM, this x, we start already much lower. We start at 5, we go to 4, potentially 3. And then with IQM, you are already very fast after 3 iterations. If you add some parallelization to the scheme, take a parallel scheme, really what it takes in the end is 2 iterations in this case. Of course, this strongly depends on the column that you are coupling. And I have not done here any rigorous comparison, and I have not fine-tuned the configuration. But still, this gives you some overview of what we can do with the same problem. A colleague of mine, and actually my supervisor now, Benjamin Lickerman, in his dissertation did such a rigorous comparison. And here you see a case that we make it heard of. This is a Chourdakis FSI 3 benchmark. This is flow in an elastic tube. And this is a lead-driven cavity with flexible bottom. And you see here how Einstein and quasi-Newton can compare. In some cases, Einstein was not even able to converge, while quasi-Newton was performing much better. And if you compare serial and parallel quasi-Newton, you see that, okay, it's not always obvious what to choose. But generally, the parallel coupling with quasi-Newton may be a good solution. So the partition coupling is a thing. It's possible. It enables many applications. You need to be a bit careful with the algorithm you're using, and there are algorithms that can perform much better than others. All right. So this was the meat of the presentation. Now some tail. So, and we will go to the questions afterwards. So there is a nice website where you find everything. You find the documentation, you find tutorials, you find all the community channels. and who is developing everything and so on. And everything you see here is just also open source. You find the repository for the website on GitHub, and whenever you find anything that you think is a typo or should be included or anything, just click edit me. This opens a pull request on GitHub. It's just markdown. You definitely can contribute to that. I'm very confident about it. There is an active community forum where many people post problems of other applications, and we try to help them. Users help other users. There is a YouTube channel where we also upload all the talks from our workshops with some delay, so you see what other people are doing with FSIs, what new features are there, so on. There is some Twitter account if anybody follows that. And there was recently a paper in the OpenFOAM Journal that I will be presenting as a poster this evening. So I think I briefly saw on my train here that this was mentioned during the keynote. I forgot here. And regarding PRECICE, I want to clarify that PRECICE is much more than OpenFOAM, right? So you can read what we are doing with it, what solvers are supported, what methods are there, and so on in this paper, which is also open access. All right, so you see me here today, and in this community, maybe you have mainly seen me, that this is just because I'm like the closest to OpenFOAM, even though I'm not really an OpenFOAM user myself. But there are also many more people. So I work at the Technical University of Munich, but there are now two more groups at the University of Stuttgart. And essentially the main person right now is Daniel Becker, that supervises most of us. And of course, Professor Miriam Schulte and our professor, Chourdakis, that was more involved in that. We do annual workshops, typically in February, and this is a photo from our workshop this February. In Munich, we hope to have another workshop soon. And as I said, everything is just because of public funding. We are very thankful for that. And yes, as a summary, we have a perspective of a developer or a user, and PRECICE gives you many features that you can just do configuration without having to write any code. And yes, you can do a lot. Of course, there are limitations, but so that would be second opportunity for questions. Please. Okay, so the question was, and there is a confusion here. So the question was, do you suggest that we use implicit CFD solvers instead of explicit, or is there something? Yes, so I want to clarify that everything I showed here was not concerning the solvers used in the codes themselves. So I did not say anything about what solver my OpenFOAM simulation was using or Calculus was using. I believe they anyway use this solvers in this case, but that was regarding the solver of the fixed point iteration in the coupling. And then, yes, implicit can be the only mathematical solution. Explicit is still there, and it's very useful when you're prototyping something, because it's much faster and you get an overview of if everything is working. But in most applications, implicit solvers make one. Yes, there are also simple applications that don't really need an implicit coupling, like the toy problem I showed in the picture. Next question. Yeah. Exactly. So the question was, I saw two terminals. Does it mean that you open a terminal, configure your OpenFOAM, open another terminal, configure your calculus, and because of the configuration, they find each other? Yes, that's exactly what is happening. They find each other just because one of the two participants, I don't remember, I think it's the first one, writes a small file with its IP address in the same directory where you have your precise configuration file. So the other one is looking for this file and then knows where to open a connection. So the one opens a connection to that socket, right? And the other one is finding the address through that predefined file and connects there. And the key here is that you start this simulation normally, as you need to do. This is in contrast to another approach where you may have a coupling server. This is something that other tools do. That essentially you need to define how the coupling that you starts the solver. And this has different problems that typically it also means that the communication is not that efficient because everything needs to go to a separate component. And of course, that you need to change how you build your solvers. So the advantage of this is that, okay, you have to add some code by calling the library to your CFP or whatever code, but then it's essentially ready because you don't need to change how you design the mesh. You don't need to define it the way that the coupler wants it. And we just run it. Yes. Okay, so very practically, very practically, you don't always need to open terminals, and you cannot do that in like in a cluster. So typically, what you can do, but we don't recommend this when you're learning, is that you can start the one solver, redirect the output to some log file, keep it running in the background with this ampersand, and then do the same for every other solver. You have 10 solvers you are coupling to do this one. Okay. A bit loud, please. I'm a bit deaf. Yes, so the question was, I mentioned that we need to define which one goes first, which one goes second. Does this matter? It matters in the sense that the second one is the one that's also computing the acceleration. This is a detail. This is now in the advanced level. When you're coupling solvers that are not load balanced, meaning that you have a flow simulation that has a very fine width and thus has 100 MPI runs. You have a solid simulation that only runs on one core. You should try to do all these operations in the one that has the many cores. So in that case, maybe you should have the fluid second, because then it's the one computing the mapping, it's the one computing the accelerator. Actually, the mapping depends. You can just move it around. But generally, you should be doing this in the participant development course. Other than that, it shouldn't really matter. Yeah, so you just guess. You say, which do I want to be the input of the other, essentially. Okay, so the question was, how does the one solver wait for the other in such a serial scheme, in the parallel? So in both cases, in the serial and the parallel, both solvers have called this advance. This advance, internally, essentially, it's like calling an NPI collective operation, where you say, I'm sending something, or a blocking operation, that says I'm sending something and I'm waiting till it has been completed to move on. And this is blocking only, again, between the processes that actually communicate with each other, not blocking for the processes that don't participate in the communication. Yes, they still have to wait for each other, but you synchronize. But you synchronize not in every time step. Usually it's synchronized after many time steps. And still, this is it is parallel. Just it is synchronizing only to exchange information, and then they move to the next solution. They don't have to wait till the other one also completes the computation. Only waits till the communication finishes. Okay, so let me maybe repeat how the schemes work, and we can continue the discussion afterwards. So in the serial scheme, you start from the initial state. The first one computes the times decides, the other one waits the time step, the other one waits. When it calls advance, PRECICE tells the other, okay, now you can continue, you can also compute the same time step. And then it reaches advance. It gives back some new solution for the displacement, for example. And then the fluid one continues, solves the next one. And then the solid also the same. In the parallel, they say, okay, the displacement I have is this, the force I have is that. Okay, good, let's go. And then they simulate at the same time. Then they synchronize at some point and they say, okay, my new force is this, my new displacement is that. You know, it's not very accurate, but let's continue. And they continue. And this is just the parallel explicit. I hope this is clearer now. Yeah, so it's definitely not obvious which of the two will be faster, because on the one hand, you overlap, but on the other hand, you may need more iterations. So this is not a new discussion. This is a usual discussion between Jacobi and Gauss-Seidel. Yes? A bit louder, please. Yes. So the question was, I saw your presentation exchanging only displacements and forces. Is it also possible to do a thermal coupling? The answer is yes. I only showed this example now because that's the most relevant. You can also exchange Temperature, heat flux, so this is a Dirichlet-Neumann heat coupling, sink temperature and heat transfer coefficient. Then you get the Robin-Robin coupling for heat transfer. Then for FSI, you can have displacement, you can have forces, stresses, you can have relative displacement. In flows, you can have velocity, pressure, their gradients, and so on. In the speed, we have not done such computations. We had to comment about this in the paper. And first of all, they solve a bit different things. So PRECICE lets you couple to external codes. And the difference is that then comes down to what methods are implemented. So PRECICE is a bit more mature as a project in the sense of years invested, I think, and has the quasi-Newton and everything else. I think that FSI also has something in this direction. Yeah, but I would not expect big differences. We have to measure this at some point, and maybe this is some work that we will do with at some point. I don't know, but it should be comparable. So what could be faster would be a monolithic approach, but then you have completely different challenges. And monolithic, I mean numerically monolithic, not facility multi-region. And I think I need to give a stage. I see people coming to me, but I will come to you and we can continue the discussion. If somebody wants a USB stick to try things out, feel free to ask me. I just need them back eventually. And I'm available to help you with anything you want regarding PRECICE over the next days. So thank you very much.